The first part is going to be trying to go through some of the production-ready multimodal agents built with AI set of code labs that you guys have been developing. I am aware that you already started with the number 1, so we're going to try to go pretty quickly to the number 2. So if you are not able to follow all of the code labs, so we're going to share the link so you can actually, in the commodity of your work, you can like try to go to the lab for yourself. So as I know, so Google is also providing the credit for you to develop this lab. And after that, I'm going to talk a little bit about how we can actually build interactive web applications focus on into multi-agent systems specifically, like focus into the interactivity of like what this kind of system requires. And so like try to kind of make system that enable users to be able to exactly know what agents are doing on our behalf. And I feel like this is a very important topic these days, which is not only to focus in build black box systems that use AI agents for automating different things, but also we need to provide generator like building rich interface to the users, a way for actually them to be able to know exactly what is going on under the hood. So this is what I'm going to be discussing today pretty much. On top of that, I'm going to talk a little bit about my experience working with agents, so you can have like a better idea of like why all of these topics that we're going to go to today are very important. So let me know if you guys have any questions. So I'm going to keep the eyes in into the chat, and also pretty also gonna be trying to check if there is any other questions about the talk today. So as Pretty mentioned, I work as a research scientist for the Texas A&M University here in College Station, Texas, and I also Google developer and Spirit AI in cloud. So this QR code is gonna take you to my LinkedIn and my personal blog website. So feel free to go there and reach out if you guys have any questions. Like um, the most important and one like really good method about to keep up with all of the new stuff in the technology is that do networking and attending all of these AI events. So that's mean that this is a huge opportunity for you guys to be able to learn all of the new state of the art stuff that is going on into the AI world. So a little bit about myself. Recently, my research is focused in building multi-agent systems that can accelerate science. Specifically, I have been trying to apply and understand how multi-agent system can help us to create autonomous systems that can process multimodal data, structured and unstructured data, and transform that into information that researchers and people and users they can actually use. So this is one of the statements that I took from the Dr. Marcus Buehler, which is a McAfee professor at the engineering school at MIT, when he mentioned that multi-agents AI enable emerging cognition and real-time knowledge synthesis in science and engineering. And we're going to see how we can actually take advantage of these emerging capabilities of multi-agent systems for facilitate how we can process multimodal data and multimodal information and make that information more accessible. And this is what I have been like researching in the last few years. So this is the project. This is one of the projects that I am working currently in the university. So we have this multi-sensor platform where we are able to collect information with different sensors, and this go beyond from using UAV and unmanaged aerial systems and to satellite data. We also use ground penetrating radar to be able to imagine the root structure of the crops. So we have a bunch of different sensors. These sensors collecting for multimodal data. Um, uh, as the result of like these sensors are able to image and to collect information in different parts of the electromagnetic spectrum. So that means that they provide different information to us. But at the end, all of these sensors are just number generators. So we need to transform those digital numbers in something that could be meaningful for the researchers and can actually help them to make decisions in real time. So, and this is what we have been doing in the last few years, trying to understand how multimodal AI foundational models and agents specifically help us to transform all of this data that we collect with this sensor in something that researchers can actually use to automate different tasks. So we recently built and published a framework that is called LegoPy, which relied on multi-agent systems to be able to transform, as I mentioned, all of this data in information that farmers and agriculture research scientists can actually use. So basically how this system actually works is that we collect this non-structured data, we store that non-structured data, and in the way how researchers and users interact with the system is they, for instance, go and open the UI and they say generate the orthomosaic, the point cloud, and the elevation map from the images that I have in this folder, but also help me to extract some features and understand what is the relationship between that feature that you extract from that data with, my crop yield on all different things, like, or help me to identify if there is something wrong with my crop. And for that, we build a multi-agent system that um, it's pretty much a set of agents, specialized agents that collaborate to be able to transform this data in something that they can, that researchers can use for decision making. But today, this talk, we're gonna focus about like the key challenge and some of the challenge that we have actually faced by building this kind of application in research. So we're gonna focus specifically to highlight some of the main issues and challenges that we face when we are trying to build trustworthy AI agents in production specifically. Um, and here I just wanted to highlight six. One is like how to making the complex data interpretable and more accessible for agents. This is one of the main problems that we have in multi-agent system these days. Like how we facilitate how agents can interpret our multimodal information. And in our context, specifically from the research perspective, so one of the huge challenge that we have found is that we are collecting information with different sensors, and those sensors collect information, like a different with different skills, uh, different, like the distribution and so on. So how we can actually integrate all of this multimodal data in such a way that agents can actually access to this information in a more accessible way, especially because something that I want you to kind of like learn from this talk today is that in the near future, the users of your applications won't be humans anymore only. You should be able to create software that agents can actually reach out and integrate to be able to automate different tasks. And we're gonna see a little bit today how you can do that. So, and in order to do so, we need to have different way to model our data independently if we are talking about structured and unstructured data. So we need to be able to model that data in such a way that agents can actually understand the format, how the information is stored, what are the dimensions of that information. Like if we are able to descriptively define our data, so agents we has been which agents that actually use LLMs, large language models, that has been trained to understand natural language. So they're gonna understand better what kind of automation or what kind of analysis they need to build on top of that to be able to automate the process that you are trying to do. So that means that this is one of the main challenges that we found, how to make complex data more accessible for agents. Just that to have in mind. Second, how we can build agents that go beyond or just calling synchronous or asynchronous APIs, where we know that the latency is not really high, and how we can actually have agents that work on asynchronous tasks that we don't really know, and we don't have control of how much time it's going to take for the agents to be able to solve that task. So we need to be able to create user experience that are asynchronous. Asynchronous means that you should be able to create multi-agent systems where if you are interacting with your agents And those agents are doing some kind of automation in the backends, and you don't have control of how much time those automation is going to take some place. We need to be able to keep the conversation going. We need to be able to the agents to understand that, and the user to understand that there is something going on in the backend, and when it's finished, I'm gonna get my response back. You know, so that's mean that multi-agent system introduce a bunch of different challenges when building software, such as those systems are asynchronous. Those systems, we don't really have the control of what those agents are in the backend. So that means that we need to have some kind of way to trace all of the interaction that those agents are doing in the backend, and we are and we need to somehow like show that to the user so the user can actually know what is going on and what is the state of my system in every iteration. So most of the examples, some of the demos and tutorials that we found out there in internet are more focused on it, like how I have an agent that call an API to get the weather data. So I have this agent that call an API to do something kind of like, we know that it's just like transactional system with a database where the latency is not really high. But whatever, I have an agent that is analyzing images, So this is one of the things that we need to have in mind. Three, how we can actually integrate agents or multi-agent systems with the legacy tools. So the one of the limitations that we have in the traditional way how to build agents these days is that, so for instance, if I have a very specialized software, that is open source and has been, I think that is someone that have the microphone on. Okay, so well, so how we can actually build agents that can interact with legacy software. And in such a case, instead to kind of like go and try to need to implement a bunch of different tools for the agents to be able to interact with this system, how we can natively implement this from the beginning. So right now, one of the projects that we are working on is how we also kind of like uh, build new protocols on top of that enable legacy software to be able to interact with agents. So this is one of the agents that we are working with the university, the ULA university, when we are trying to come with an approach for like make agents to be able to interact with legacy software. And in that way, we don't really need to implement thousands of tools for those agents to be able to interact with this kind of tools, information. So another challenge is like how we can ensure transparency and traceability. How we can move beyond of like building this black box system that we don't really know how like what is going on under the hood, and how we can actually rely on the different tools that we have out there, some of them open source, some of them commercial, that enable us to be able to have a system that is more transparent when the user actually know what is going on in the backend. So this is another challenge that we have found working on some of the project that we have like worked on. Another huge challenge these days is reducing hallucination and how make this system more unreliable behavior. Like how we are actually made those agents hallucinate less, and how we can make these agents to prevent to incorrect reasoning, tool misuse, and just like hallucinate generating the output that we require from this system. So, and finally, another challenge that we had found is like how we design effective human agents interfaces that are responsive, that take in consideration that multi-agent systems are asynchronous, and we need to have a way to actually stream in real time the status, like what the agents actually are doing, and how we can actually create tools that are more informative, and where the users can actually know exactly what is going on under the hood, and they have the control of what they are doing. So this is one of the 6 challenges that we have found of building AI agents, specifically in our context of like building multi-agent system for research. But today we're gonna focus in 2 of them specifically. One is for like how we can reduce hallucinations and how we can evaluate these systems before to actually deploy them in production. And on top of that, how we can actually define effective human interfaces relying on protocols such as Agent AG-UI. So to start, we're gonna focus in this section of the presentation in how reducing hallucination, or at least how we can actually evaluate this multi-agent system in such a way that we can have metrics that help us to understand better. So where is there an opportunity for us to improve the performance of the multi-agent system itself? Like, and uh, one of like the kind of like the trend that we had found in evaluating multi-agent system recently is that we tend to fall into the what we call vibe check trap. And vibe check trap means like we think that an efficient way to evaluate a multi-agent system is just like interact with the system and prompt the system multiple times and try to come with the best prompt or the best system prompt for those agents until like we get into the point that we got the output that we expected. But this is not actually a very deterministic way to evaluate this multi-agent system. And on top of that, we need to be aware that we are moving beyond of like having deterministic system into having like probabilistic system where we know we don't know exactly like what is the kind of output that I can expect. And for the same input, always I probably gonna get different outputs from that. So that means that we need to be able to have more deterministic ways to be able to evaluate and check the performance of my system. And by doing so, we can actually have different or implement different evaluation mechanisms and different methods to fine tune these models or this and the agent itself as a system to be able to have a better implementation before to go to production. So this is one picture that showcases what we generally do. So we build a system and then we start manually chatting with the agent to verify the quality of the output that the multi-agent system is generating. But we're gonna very soon hit the wall because like we don't have a deterministic way, as I mentioned, to be able to identify where my agent is failing. And this actually happen more often when we have systems that go beyond of like one or two single agents. When we have multiple agents cooperating each others or building agents that they can actually collaborate. So currently there are two different approaches to do or evaluation or evaluate multi-agent systems. One is evaluate the agent system developed, and two, we can actually make the evaluation process of the multi-agent system part of like our CAD pipeline. So what actually that means is that one is that the offline experimentation is very useful and help us to kind of like identify some patterns, mostly in the generation phase. Not that much in the reasoning aspects of the multi-agent system itself, but the offline experimentation helps us to identify some trends, and we spend hours and 1 hour chatting with the system and do prompt refinement and rapid iteration, and we try to kind of like do a lot of prompt engineering and do all of this kind of stuff. Sometimes we actually go beyond and do fine tune of those models, applying uh, different post training techniques, like reinforcement learning or even like just using the traditional fine tune methods such as LoRa. Like we can fine tune those models and those models are pretty much like what actually power those agents. So there are different ways to find tune the system, but offline experimentation is still being like a very important steps, and it's not wrong to actually try to chat with the system and try to identify patterns where like when I see or when we see that the model or the system is not actually working properly. However, so we need to have a way to actually um, like make implement a more deterministic evaluation strategy that eventually we can actually automate that process and introduce that as a part of like our CID pipeline, where in our CID pipeline, what we define is all of the steps that my system is going to go through before to actually reach production. So that is what we actually implement. Okay, every time that I do a commit to my main branch in my GitHub repository, I would like to run these uh, different like actions or GitHub action or pipelines in the backend that I would to automate different aspects of my deployment process, right? So this is around like the operating it's around about the all of the MLOps steps that we can actually do and to be able to automate the coming from the development product that we just create and putting that into production. So this is what we call continuous evaluation, you know. So in the lab that we're gonna see today, and we're gonna right away jump on that, is that we're gonna see how if I had my system, I develop my system and I want to deploy that using tools such as Cloud Run. You know, if you're not familiar with Cloud Run, it's one of the Google services that make easier to deploy um, any kind of software in production. You pretty much put your software, you take your software and put that into a Docker container, and you deploy that pretty easily into Google Cloud. So, so, um, so we're gonna see how you can create these CI pipelines when you can make so the system, the multi-agent system itself, go through like a different set of checks that you can do in terms of like evaluating, for instance, the hallucination and all of these kind of like evaluation, the reasoning traces, the agent's trajectory, for instance, when it's like doing the tool calling and this kind of stuff, how you can grab all of this stuff into your deployment pipeline, and so how you can take advantage of the automation that provide um, all of these ML ops tools, to be able to have a pipelines that are more deterministic and make that my system that make that give me the confidence that my system that is going to production is aligned with all of these metrics that I define. So there are two ways to grade agents' performance. One are, as I mentioned, the deterministic ways. So when we have a different ways to take the output of those independent agents, and then there are different uh, metrics that I can apply, pretty much like different equations or like so that you can just take the input as the input and apply that function and then get like a score. There are different functions that we're gonna go through some of them in the lab. But in the other side, we also have model-based graders. When we have another, this is what like commonly people knows as LLM as a judge. So you can actually take or have another model or even like another agent pilot for evaluate the output of those systems in order to check that the output that your multi-agent systems actually are generating are more aligned with the output that you expected from your system in production. So that means that we have these two different ways to evaluate agents. One using code-based deterministic metrics that are more similar to what we have traditionally in the machine learning uh, method that we used to use when we have like all of these different methods such as R square, all of these kind of like mathematical tools that we can actually use to be able to evaluate the performance, the accuracy, all of this kind of stuff. But we also have these days these deterministics approaches when we can take advantage of the reasoning capabilities and the emerging capabilities of large language model to use them as a judge and then be able to provide a structured information that we can use to do another level of evaluation into the system and identify early patterns into the application before to actually go to production. So this is some like the two different approaches that we have. And there are different tools and there are different tools to do so, like we're gonna see that today. So for the demo part, so we're gonna move pretty quickly into this code lab. If you guys have access to it, if you don't have it, I'm gonna share the link in the chat. Okay, so I just shared the link, and we're gonna go to this pretty quickly. If we are not able to cover all of the points here, so it's fine. As I mentioned, this is something that you can just like in the commodity of your work, like take over and then work on it and then deploy that. So Google actually gonna provide the credits to you, so you just can actually use and take advantage of them to be able to see this running in production. And this code lab is built on top of the previous lab that you guys worked on. So specifically, what I mean with that is that in order for you to be able to follow this lab, you just have went to all of the previous lab, which is I think this one. build a multi-agent system. However, just for the information, for this lab specific, you don't gonna need to get back and try to finish and rush and like complete that lab, because this lab is gonna provide all of the functional code for those that were not able to finish the previous lab uh, yet. Okay, so we're gonna start this lab with the assumption of like we have this multi-agent system that help us with the course generation. It's a multi-agent system where you just pass a topic, and based on that topic, we had four agents specifically: the research agent, the judge agent, the content builder agent, and the orchestrator. And these agents pretty much like within this multi-agent collaboration system, what they're gonna do is that they're gonna create an end-to-end course with all of the information and so on. I guess that you guys saw that in the previous lab. If you didn't, so make sure to check it out, that code lab as well. So we're gonna start with an introduction. Pretty much what we're gonna do is that we're gonna build a continuous evaluation pipeline for our agent. Let me increase a little bit. So we're gonna build a continuous evaluation pipeline for your agents. When you're gonna learn how to deploy your agents to a private tech revision on Google Cloud Run, take advantage of the shadow deployment mechanism that Google Cloud Run has. So just to put into the context, if you are not familiar with that, in Cloud Run, every time that you deploy your application and create another version of your service, so it's kind of like having another version of that. So that means that you can track what are the versions that you have deployed on productions. And this is beneficial in this case because so we're gonna see how we can integrate into a deployment pipeline. Um, like an evaluation component that help us to evaluate the system and identify if the system have some hallucination issues or have like some problems in the early stage before to actually create another version or create another version of the service and production. So pretty much just to make that easier to go through is like we have this multi-agent system, we deploy that in Cloud Run, but before to actually deploy that into production, we're gonna add a kind of like checks component that is take advantage is gonna use the Vertex AI evaluation toolkit to run a bunch of different metrics into the system. And based on those metrics, we can actually define if we wanted to move that version into production, or otherwise we just hold the version for a while and we can actually experiment it more and identify which actually are the problems that I am having before to go to production. So then the idea is to learn how we can take advantage of the shadow deployment and target versions of Google Cloud Run to run an automate evaluation suite against that specific revision using Vertex AI generation evaluation service. And we're gonna also we're gonna see how to visualize and analyze the results and how integrate that into your CA and CAD pipeline. Okay, so some of the core concept we already went through all of them, as I mentioned before. So we have two different ways to like play around and evaluate your system before to actually go to production. One is like doing offline experimentation, which is pretty much do a lot of prompt engineering and like chatting and by kind of like interactions with my system and try to identify some trends that can help me to identify issues in the evaluation process. But we're gonna see and we're gonna focus in this code lab specifically into what we call continuous evaluation, when you can automate the process of evaluate all the system and identify and compute different hallucination metrics, such as hallucination, tool calling traces, reasoning traces, all of this stuff, and how we can use that to make the decision if we wanted to move into production or not. And this is, and we talk a little bit about the by-check trap, what actually that means. And we know that we have two different grades of agents performance metrics, deterministic and probabilistics. So feel free to go through all of them. We briefly already touched on these topics, so we don't gonna like get back to went through all of them again. So then let's start working on the lab. In the lab, start like making sure that making sure that you actually have access to your account. So I'm just gonna run this command. So let me see if I can actually split this into. So technically, if I have this project and this, okay. So as you can see here, I have in the right side my GCP account with my project, which is called Build with AI project. And so I'm just gonna open the terminal. So my suggestion is use the editor directly because you can actually run the commands on the editor terminal, but at the same time, you can actually see the code. So I'm just gonna click here in the open editor. And so we're gonna start working on the lab them. I'm just gonna close this. And so this is how the Cloud Shell editor looks like. So here in the left side, it's just kind of like playing around VS Code. It's pretty much like an instance of VS Code running in Google Cloud, and when you can actually provision a virtual machine that is going to be running your stuff. So the first thing that we're going to do here is that we're going to click here in terminal. I'm going to open a terminal here. Okay, so I'm in my terminal. And then I'm going to start running the commands that I have in the left side to the. So the first thing that I need to check is that I am logging into my account. So I'm just gonna click here and I say yes. So this is gonna just like tell me to kind of open this link in another tab, and then select what is the account that I want to kind of play around with. So then I'm just gonna continue, and then I'm gonna copy this token that has been generated. And I'm just gonna get back and paste that into my. Okay. So the next step is that I need to actually set my default project. So the easy way to check that what is your default project right now is you can just like go and type gcloud config and then get project. And as you can see, it's telling me that this is the project that I am working right now, build with AI project, and I confirm that this is the project that I want to work with. This actually mentioned here that it is not set. You need to run the command and make sure that you specify what is the project that you want to work on. So then the next step is you just need to go and download the code repository for this code lab. So I'm just gonna copy this link here and paste it. So this is just git clone from the repository that we're gonna use for that and jump into the folder. So then as you can see here is the code, okay? So as I mentioned, even though if you haven't finished yet the previous lab, don't worry about it because that code has been provided here. You know, like all the complete implementation of the multi-agent system built on the previous code lab is already here, so you don't need to worry about it. Okay, so then when I have that, I am already in my build with agent evaluation lab project. And so now I'm just gonna create an environment file with these variables, which include what is the project, the region, the location, and so on. And as you can see here, so this file is created based on the output from these commands that you can actually independently run to be able to know exactly what is the project that you have defined as default, your region, and so on. So I'm just gonna copy this and paste it in my terminal. And what is gonna happen is that it should create a new file here into the agent evaluation. Let me see if I can see the file there. Okay, as you can see here, there is a new file here, .m. So I can actually pretty quickly to check that out. make sure that the file is there. This is the more important point. Sometimes, so even though the file is there, you cannot see it. So it's like a more like a refresh issue. But okay, so the next step is like open the Cloud Shell editor. We already opened the editor previously, so it's no, let's don't worry about it. So then we're gonna run this command uvsync, and what this uvsync does is like this use uv, which is like command line terminal tool that you can actually use to manage your Python code environments. Specifically, this tool have those two functionalities. One is that allow you to install and run and switch between different Python versions, which is something that you should previously used to do with tools such as PyM, but right now UV already integrate that. But on top of that, like you can use UV also to manage the dependencies that your project needs in a folder level. So that means that you can create a folder, and what is going to happen is that UV creates a PyProject TOML file, which is a standard file where you can actually define the dependencies of your project itself. And then based on that, you can actually have control with which Python packages you need or which dependencies you actually need to be able to run your code. So I mean, UV is a very practical tool because combine the job that you used to do with PyM and Poetry independently into one single and standalone application. So if I run the UV sync, what is going to happen here is that it's going to go and read this file, PyProject YAML file, and then it's going to install all of the Python packages that you need to install in your environment to be able to run the code that we're going to try to run today. So the next steps is going to be understanding safe deployment. So we already talked about the revision tags. As I mentioned, Cloud Room provides this mechanism that every time that you deploy in production a new version of your service, is going to create a shallow tag revision. So that means that you can have multiple revisions from the same um, service. And this result very convenient for this exercise, because what we're going to do, as I mentioned, is that um, pretty much what you do is that before to deploy your service in productions, you're gonna pass your multi-agent system through a set of different evaluation steps, which use, in this case, the Vertex AI evaluation service to generate a bunch of different metrics, and based on that, you decide if you want to create another revision or not. So otherwise, well, the deployment is gonna be halted. Okay, so we're gonna go directly to so the CID workflow deploy is this one. So we do a commit. So once we change the prompt, so we do some kind of fine tuning in my system. So then what is gonna happen is that that commit is gonna trigger a deployment of a new revision with the commit hash as a name or as ID. So then once this is actually run, so this is gonna generate a new version, and then that version is gonna pass through a bunch of different, as I mentioned, evaluation steps, and then once you are one kind of the pipelines, make sure that the performance on the system is the performance that you expected from this multi-agent system. So uh, it's gonna promote this version and make this production, make this service, or make this version like the production and the first revision to use in your production system. Otherwise, if it doesn't work, so you can actually feel free to do a rollback if you need it. Otherwise, you can also do this into the system. Okay, so the first thing that we're gonna do is that we're gonna open this evaluate file that is right here. Okay, so this is the file that actually create run all of the evaluation pipeline. So as you mentioned here, the deployed SH takes care of the revision deployment with no traffic tab option, and there is already running service, it will not be affected. So the new hidden revision will receive no traffic unless you explicitly call uh, this revision tag or make it available in production. Okay. So open the script and automate the process. This is just one telling us that you want to understand what is happening. Okay, so now it says open the evaluate agents, and so we're gonna do some changes on that file. So just gonna evaluate agent, and then so you can see here that this actually import some metrics that have been implemented in these files, like tool metrics, for instance, when you can actually go and see how the trajectory precision function is computed. You can see that this is a deterministic function, but based on the output from your agent, it can actually infer if a function call actually was made, and if that is the case, it's gonna try to kind of like, based on the output of the multiple iteration that the system is go through, so it's able to identify what is the score based on like if the system correctly name that the tool that were expected based on the ground truth data that's provided. So then this is very important. You can see also here there are two files JSON. Those are the ground truth data that has been using for in this case to do the evaluation process itself. Remember that for as is traditionally machine learning, so we always need to have a ground truth data to be able to evaluate, in this case, the performance of the model itself. Okay. What else? So then we're just gonna keep with them. You will see import and setup, but metrics and execution logics are missing. Exactly as we can see in this file. So we have a bunch of different. We have like some imports here and some environment variable defined there, but we don't really have any code here. So that means that if we try to run this evaluate SHA file right now, what is going to happen is that it doesn't have anything to run here in this file. So this is why we need to change that. And what we're going to do there is we're going to implement the these three levels of evaluation, like final response match, tool use quality, and tool use trajectory. So then for the custom tool use trajectory metrics, so we create a set of Python functions. So for the independent evaluation metric that we're gonna run here in the evaluation, just gonna go here to share evaluation tool metrics. Okay, share evaluation tool metrics, and we can see the implementation of those functions there. Okay. So okay, we finished. We create a custom function metric. So it's good. So there is another function here that was implemented, which is get custom function metric, which converts a Python function to a custom code evaluation metrics. This is in the case that if we wanted to actually create a custom evaluation function that is not being considered in this code lab. What I mean is that there are Vertex AI evaluation service already have some predefined metrics that you can actually use it. Like you can, indeed, if you go to the generative AI evaluation service, you can see there are a bunch of different metrics that you can actually generate, like evaluation with adaptive rubrics with this tool. But this also gives you the option that if you want to implement a very custom evaluation metric that is not there, you can actually do it. Like so that means that make sure to check some of the evaluation metrics that you can actually use with the. Okay, so getting back to the lab, he's showing us here that if we want to implement a custom evaluation function, we can do it. So and he can actually giving us an example of how to do it. But the most important part here is that we need to add those metrics into the evaluate agent file. So which is this one, evaluate agent file. I mean that I just gonna he said that after the main entry point instruction here in the Python file, I'm just gonna copy these metrics and we're gonna paste it here. So this first iteration of evaluation, what it's gonna do is gonna load the ground truth data from this file. This was, for instance, specifically for the researcher agent. I define this arrays of metrics that I wanted to calculate for that agent interaction. So this includes final response match, tool use query, or two custom function metrics that were implemented in those files that we previously checked, these two metrics. One to evaluate the trajectory precision function and the trajectory recall function. And this is more like a way to measure like if the agent is properly doing the function call, but but also like is following the trajectory that is expected. When I talk about trajectory, is that every time that you pass you pass like a question or like a task to the multi-agent system, what is happening is that from that system, a bunch of different reasoning steps are generated, which can be, for instance, include code to the pass the information to the research agent, call this function, and so on. So you can actually evaluate how accurate or how is the performance of these agents calling this function and stacking all of these functions that you expect to the agent to be called. So then here, these evaluate agents use the uh, Vertex AI evaluation services to run all of the metrics and to generate the, the tracing and the logs into the system. Okay, so we just keep going, and then so then once the evaluation is actually run, we can add this condition here, and this condition is pretty much saying that, for instance, if the mean value of the evaluation results, specifically for each metric, each metric generate that score. So what I'm doing here is that I'm gonna make sure that after running the agent through all of this ground truth data, generating those scores for every iteration. Every iteration means like for every prompt that we pass to the multi-agent system. So we're gonna get an output. So we compute the mean for all of these values, and we make sure that the mean is if it is less than the metric threshold that we define, it's actually that means that the researcher didn't pass the test. So that means that we can just inform to the user that unfortunately, after running the evaluation metrics, so the multi-agent, the researcher agent specifically is having hallucination issues. Something that to have in consideration here is that you can notice that we are doing the evaluation for each agent independently, so this is something very important to check there. Okay, so now we're gonna copy this other optional set of metrics that you can actually generate for the orchestrator. But it's very straightforward, as I mentioned. So we have a multi-agent system. We have this evaluate agent file that is going to take each agent and it's going to use the Vertex AI evaluation service to generate a bunch of different metrics. So then programmatically, we're going to check that those agents are aligned with the kind of threshold that we designed. Otherwise, it's going to generate an error. Sorry, what is the app itself about? What is the app itself? So you mean it's not clear your question about what is the app itself, but
sorry, not what I mean is not the evaluator itself or the LLM portion, but what does the app do, or is it just the evaluation kind of app, like on synthetic data or something? Like what do we evaluate? What workflow we evaluate?
Okay, so this is a good point. So as I mentioned in the previous lab, we built this multi-agent system, right? That is formed by 4 agents. The researcher that, so what we are doing here is we're atomically, we are evaluating every agent independently. For instance, this is the data that we are using to evaluate only the research agent. And if we go to that file, this is the ground truth data that we are using for that. And this is this for the orchestrator to check where he actually wrote this prompt to, like in this case, it should be uh, wrote this to the research agent, and this is the ground truth data for the researcher. So that means that here you can pretty much specify what is the agent that you actually wanted to evaluate. You know what I mean?
We're building the engine, but for anything.
Exactly. So this all of these codes, if you go to the implementation of it's just let me check here the function itself. If you go to the implementation of evaluate agent function,
Yeah.
so you're gonna see that it's an agnostic function that you need to pass the URL of the where the agent actually is running, and then in that way, so the agent can actually communicate with that service and run all of the evaluation process. You know what I mean? So you
Yeah.
take the agents, you make this agent available, you deploy that to Cloud Run, and then so once you have the URL, or you have like a way to actually reach out and access that agent. So then the next step is that you call this evaluate agent, and you make sure to specify what is the agent that you want to evaluate. This is what I pass in here, the
Yeah.
researcher URL, and then based on that, this um, as I mentioned, agnostic functions can be specialized or can be defined for every agent. The only thing that actually changed is the parameter. You see that this is the research URL and this is the orchestrator URL.
Yeah. Okay.
Now that what we're gonna do is that we're gonna run an sh file that run all of those evaluations, and it's gonna save all of the results of the evaluation process itself, and then we can actually visualize the results and make any decision that we want. Okay, so this is the next step. We're gonna say that here. And then, so understand the evaluation code. So as I mentioned, the evaluate agent function is an agnostic function. It's a function that can be used for any agents at all, as long as you have the URL of the agent itself. What it's gonna do this function internally is gonna read the ground truth data. And for each prompt, it's gonna run parallel inference. So that's mean that imagine that you have 10,000 prompts. In parallel, what is going to happen is that this function is going to dispatch a parallel inference process where all of these prompts are passed into the system to the agent itself. And then for each output, it's going to call the vertex AI evaluation to generate the metrics. And then after that, you're going to be able to access to those metrics and make this programmatic checking here of if those metrics are the metric that you expected or not. So again, you build your agent, you create your ground truth data set, you do parallel inference. The parallel inference is a very key component here because you don't want to hold or you don't want to do a for loop for all of the prompt. Imagine that you have a data set of 1,000 prompt. You don't want to like hold the user on that. So then you like evaluate that in parallels. And once you get all of the data, so you can actually check some metrics such as the mean, the standard deviation, or whatever. And then so the agent info API. So the perform accurate evaluation, the evaluation service needs to know the agent's configuration. This is why um, in the agent ADK app, which in this case actually take each agent and expose that agent as a service. So we need to implement this function. And this function is gonna make sure that when we do perform the evaluations, so he can actually double check that the agent that the evaluation is being run is what the evaluation process is supposed to do. Okay, he's just explaining me here what is going on. And then finally, once we have this in place, we run this command evaluate sh. So then we can run this, and this is gonna start enabling the stuff that I need, running the evaluation, checking the existing deployment. If there is not any deployment there, it's gonna dispatch a new deployment in Cloud Run. So that means that the agent is gonna be available for, you see, here it's trying to deploy the researcher. So then after that, it's gonna run the evaluation checking, it's gonna generate the metrics, and then we're gonna continue from there. I am sure that I am out of time, so I just wanted to pretty to let me know. Yeah, I know that I'm maybe out of time, so I'm just gonna stop here. So I just wanted to briefly. This is kind of like a long um, code lab, but I briefly explain what is going on here. I wanted to make sure that at least you have an idea of what we are doing here. So when you try to kind of like do this slide by your own, so you guys have a better understanding. As I mentioned, what we did here is that we built a multi-agent system using ADK, which is a set of multiple agents working together to generate the course content based on the topic that we provide in the UI. So what we are building here in this code lab is all of the evaluation pipeline. So it's just running this evaluate file. What we would actually do this is take every agent, deploy that in Cloud Run, pass that through like this evaluation process using the Vertex AI um, um, evaluation service, and then generate the metrics, and we can move from there. So you can just go open this code, play around, and let me know if you guys have any questions. So I wanted to close my presentation pretty quickly with the next issue or challenge that I wanted to kind of like approach today in this presentation. That 1 hour is a very short time to actually go through all of these two topics. But so the other main challenge that we found is like building user interfaces that they can actually help us to better understand how what the agents are doing under the hood. And for that, I use the protocol that is called AG-UI. I'm not going to touch that. To close my presentation, what I wanted to show you is that I recently published in Google Cloud um, these two articles, building interactive agent application using ADK. This is the basic, and this is kind of like the block that set the foundation. This is one single agent working with AG-UI, which is the protocol that standardize the interaction between the agent and the user interface. This one is more like how to combine in one single multi-agent system ADK, NCP, agent-to-agent, and AG-UI. And pretty much what the kind of application that you're gonna learn how to build is that. Let me do this pretty quickly. So this script, what it does is like run all of the NCP server, the agent-to-agent, agent-to-agent agents, and then run the UI. And this is how the UI looks like. So this is what I'm talking about, like the kind of UIs and user experience that we need to build. So if I ask what is the weather in San Francisco, what is going to happen is that this prompt is received by the orchestrator. So the orchestrator found out that he need to further check with the Max agent where are the location of San Francisco. So then he generated a function call, so the user can actually see here with a beautiful component what is going on. But then after that, he figured out that he need to then, once have the latitude and the longitude of the location, he can call the weather agent, and he can actually see what is the response here, and we can actually present that to the user in a more user-friendly way. So you can actually see here not only the outputs, the function calls that are generated, but on top of that, so you can actually see all of the interaction between multiple agents working together. So all of this information is available in the blog post. I highly recommend to check it out. And with that, I think that this is all that I wanted to share. So this is the kind of like system that we expected to develop. This is one of the projects that we are working here in the university as a research side project. And so this is an agent that is able to interact with other software. Let me check. So you can actually see in real time what the agent is doing and how the agent is actually interacting with the specialized. But it's something that we can leave for another talk. Thank you so much for the time. I took like 13 minutes more. I apologize for that, but this is so much content to be covered in 1 hour. I did my best, but all of this information is available, public available. So let me know if you guys have any question about that.
Thank you, Henry. And we do have some questions, and I believe we'll cover next 5 minutes addressing them. So I'll start with, first of all, with the most common question that we always have in sessions. Would we get access to these slides from you?
Yeah, so I'm gonna share the links with Pretty, so really can share with everyone. And for the articles that I just mentioned here, when I explain how to build an end-to-end system that cover all of the protocols working together, NCP, agent to agent, AG-UI in a single system, so you can check it out those links.
Thank you. Now moving on to the Q&A session specifically, could you elaborate, this is by Daniel, could you elaborate on LoRa and how it's used for fine-tuning any model, perhaps from your own experience?
Well, so QLoRa is the foundation, the math foundation behind of that in mathematically speaking is that you have this huge model of billion of parameters that can be compact in this weight matrix that is huge, you know. So instead to you do traditionally what you used to do in transfer learning when you use or in like traditional fine tuning in deep learning architectures such as convolutional network with when you update all of the weights of the matrix in one single pass iteration of the model itself, because these matrices are huge, as I mentioned, because they're like huge model of billion of parameters. What you do is in math, there is a technique that is called matrix decomposition. You know, using techniques, for instance, which are singular value decomposition, you pretty much can find a set of matrices that's kind of like you have like a original matrix, and in singular value decomposition is you decompose the matrix into soon matrices that with an small size. It's kind of like reducing the dimensionality of that, and by representing kind of the statistical properties and mathematical properties of the distribution of the original matrix in a more small space. So that means that so then you represent all of those weights in a low vector space, you know. So once you do that, instead to you fine tune all of these billion of parameter of update all of those billion of parameters in the fine tuning, you only focus on in those small representations that try to compact the more important weights that are in that particular model, and you can define which largest you can actually pick. So LoRa is pretty much this is called PET fine tuning. It's a parameter fine tune optimization. It's a technique when instead of you update all of the weights of your model as a whole during the fine tuning process, you first apply the matrix decomposition to be able to take all these huge matrix and of weights of the model itself and project them into a more load representation, and then so you have just you update this matrix, and then through the inverse operations, so you can actually fuse those weights back into all of the original matrix. This is a little bit technical, so I think that we need to have another talk to talk about parameter efficient fine tuning.
No. I appreciate the sharing the article. Yeah. Trying to lower the dimensionality and trying to limit the vector space. I will do a debrief. Thanks for your time. Yeah, that's interesting.
Sure. Mm-hmm.
Thank you. Thank you, Daniel. I see AM has raised their hand. Do you want to unmute yourself?
Yeah, that's Andrew. Yeah, sorry for
Andrew. Sorry. Yes.
Yeah. Thank you so much. And Henry, it's you have a wonderful blog and personal site. It's a lot to read, and your bio is like what I would be in an alternative life, a next life, so we focus on Vertex AI, right? Because it's Google and so forth. Like, my high level question is, what would it like for this app? What would it take to do it without Vertex AI?
Yeah, so there are some open source. Indeed, you know, like ADK itself, the ADK, which is the framework that we use to create the agents, is open source. He already has some implementing all of these evaluation techniques, so you can actually use them. And you can run ADK in every cloud, you know, like it doesn't necessarily need to be running for the evaluation part. But also there are some other Python packages. For instance, like there is one really cool that is called Ragas. This is a framework that helps you to do a bunch of different evaluation as well. But yeah, so overall, so these parameters are well documented. So there is a really good open source project out there. Honestly, what Vertex AI actually provides is more like a cloud managed optimal way to run this evaluation in a cloud environment. But you can do that if you're on-premise infrastructure, you can run this locally, so it doesn't necessarily need to rely on the Google Cloud stuff.
And we can do versioning like with Ragas too. And right, so
for versioning, for instance, one of the things that you can do is MLflow recently also have a lot of evaluation things. MLflow is open source as well. So they are doing a really cool stuff for agents itself. So you should give a try to this. This is something that you can deploy in your own infrastructure. You don't need to have any cloud for this. But they have recently implemented a bunch of different observability of this kind of stuff. I actually right now working on contributing with this, and they have a bunch of different evaluation techniques as well. And all of this is open source. You know, like as I mentioned, if you have a good server and you want to run that by your own, you can do it. And it's more like an agnostic approach. You know.
Thank you.
Sounds good.
Thank you, Henry. And we'll just quickly take one more question, and rest of the questions I'll share with you on LinkedIn. And we usually go by the discussion board, and I would let you answer them on GDG discussion board. But this is a question from Sirisha. Can we use Raga's framework with ADK for agent matrices like topic, adherence, agent goal accuracy, etc.?
Yeah, Ragas is more focused on context generation. It's more like from the deterministic kind of metric that you can generate. If you go to the reference, so most of the metrics that they provide are more focused on in like RAG systems or like retrieval augmented generation system of traditional elements LLM system where you pass the prompt and you get an output. But this is something that is you can actually integrate for evaluate agent as well, especially for RAG agents, for instance. You know, these days RAG is still around, and this is one of the ways that we actually have to like provide agents with the a way to ground the output that they generate. So you can use tools such as Raga to evaluate the performance of that and integrate that into your evaluation pilot. And MLflow also have that integrated here on the agents with MLflow.
Thanks a lot, Henry. This is great. And with that, we'll wrap up our session 1, and we'll move towards our session 2 now.
Good. So, all right. So I know that you guys have been doing a lot in these 2 days. So first, I really thank you guys to be here. I know that it was not a cool morning, but we need to go on. And also, I wanted to finish this whole Build with AI session a little bit with story, like how we are moving from using models to actually be the psychologists for LLMs. So the story that I want to talk to you today is going to be about how do we actually try to understand what is happening under these black boxes when you are using agents, and exactly how this aligns into research, and how you can actually use these kind of interpretability features into building models that you can actually steer to whatever behavior that you want to have. So think about like this is going to be a tour of how to become an LLM psychiatrist. So QR is there if you want to follow along the lecture. There's going to be a collab at the end of the 30 minutes. And these lectures are based on Anil Nada, which is one of the biggest interpretable research at Google DeepMind. So with that, let me see how it goes. Okay, where is my notes here? So what is actually mechanical interpretability? So the core hypothesis of this field is that models learn human compressible algorithms. And these are really a difficult fact sustain, right? Like models do not have any imposition that they should have like concepts that are human related. And my goal or my hot take on this lecture is that you actually that this human interpretability can make sense. And this they learn this structure because it's useful to get in the laws what they have access to go to predict next token go low. So and it's our job to reverse engineering and how to make it legible. So for example, the hypothesis that model learn human compressible algorithms. If you take a look at the development of this area, when at the University of Toronto, when we trained one of the first models to actually learn what is on this image, that it was called ImageNet. So ImageNet in the 2000 was a very challenging data set in which, hey, is this a what? So I give you an image of a car, and then you're going to say, okay, this is a car, this is a rabbit, this is part. And what we found is that at the beginning of these neurons, it seems that the LLM gets activated, or they seems very putting the focus into learning this very special concept. So it's there is a window, there is a neuron that is responsible for understand the window, there is a neuron responsible for finding the body of a car, and there is a neuron responsible for the wheels. And the union of these three things, of these three neurons, it gives you that it's a car detector, so you can actually pinpoint what was the neuron or the feature that activated that. Hey, this I'm going to be activated if I see that my input image is a car. So our goal at this moment is that sometimes we just train these models and we have only the weights. So how we can actually get from those weights to something that we can understand. And if you come from a cybersecurity prospect, or if you want to see the connection between cybersecurity and machine learning, is that we try to reverse engineer the neural network. So we have the weights, we have the models, we want to figure out what were the concepts. So like trying to learn what are the source code. So I'm telling you, this is not very new, or this is not something that it's a question that has been on the last few years. This has been for a decade, and a really good experiment that I encourage you to do is that take the ImageNet dataset and try to train a convolutional neural network. You're going to find that in the first layers, you're going to find that there is linear detectors. That is that they're going to learn very concepts of what is a line, what is a circle. In the second layer, you're going to find that it's going to use the information of finding lines and circles to actually find the characteristics and the features that makes an image complex. And as soon as you go in depth in the neural network, you're going to see that the combination of these features is going to give you things like, hey, if I'm trying if I try to understand if it in an image there is a dog or there is a cat, we're going to see that the responsible of those neural networks of those neurons to be activated are going to be the face of the car, the face of the cat, the face of the dog. And this is something that you can replicate very easily on AlexNet. That just ask Gemini or Claude, hey, give me a neural network, a convolutional neural network that can understand, that can identify dogs and cats, and you're going to see that these features appear naturally. Not only in image recognition, you're going to have this task. It's also in autonomous driving. So here's a robotics company that is trying to do food deliveries in actually they are in Vancouver in the library of the UBC. And what you're going to see is that at this part in this architecture of the neural network, in which you have an image alongside with how left or how right a human pilot will drive, you're going to see that some characteristics, some salient characteristics of this image are going to be the boundaries. So the convolutional neural network wants to keep in center these robots, and the activations on the image are going to be like the boundaries of the sidewalks. So neural network seems to be having this understanding of human concepts. So again, this is a very strong claim. I'd like to convince you that it's actually possible to understand all this crazy matrix multiplication that is going inside on trained neural networks. And if you ask on in many laboratories or at the university, there are people that could tell you, hey, this is just a bullshit area, this is a bullshit field because it's only like a bunch of matrix multiplications. So I wanted to show you that in a very simple example that it actually can be correct. So our setup for today is going to be this. Like this is one of the most. This is a basic LLM or it's a basic LLM that is trying to learn how to do modular addition. So we have two numbers, we add it and we apply the modulo 113 part. So what we are having is that we have all the components of a modern LLM. So we do positional embeddings, we do the token embedding, we generate an attention head, we generate an multi-layer perceptron, then we do the embedding and we get the results. So we're trying to understand, hey, when we give this task to an LLM, how does he actually learn to actually do this operation? And the attention is the most fundamental block of an LLM, and the MLP is like the most fundamental part of machine learning. And just to give you a sense, if you look at the paper, and I'm going to give you the paper in a few slides, the algorithm is very simple. So the LLM, we learn how to, by looking at as a spoiler, by looking at the interpretability, this part looks like the LLM is doing the following operation. It learns to use trigonometry and trigonomic identities to actually. So the embeddings look like they do a Fourier transform. They use some trig identities. Finally, they do some multiplication, and then they do some voodoo magic, what I call like complicated trigonometry identity to just get the logics. But it's something that I wanted to show you, that this is something that we took an LLM and we were able to figure out like what was the source code of what this LLM was trying to do when it was learning how to sum two numbers and do the 113 modulo operations. And why is this important? So we see there is a mystery right now in machine learning, in which whenever you're trying to do this kind of learning this operation of learning like numerical algorithms in machine learning on LLM, it looks like if you overfit your model and you keep fiddling with your upper parameters, and if you keep continue training, at some point, even if you take a look, the train and the test loss are huge. As soon as some point goes on, the model actually learns to generalize. So it's something that it's completely weird. It's like when you learn how to do machine learning, you try to avoid this gap between train and test, but somehow in these small models and learning numerical algorithms, it seems that it generalize. Just keep living running until you hit this sweet spot that it generalizes. So how we actually know that we can actually learn or understand this mystery? So first of all, if we take a look at how the embedding looks like, you're going to see that when we extract the embeddings of the training neural network, it looks very periodic. So the embedding recalls this operation that takes like the tokens that go from 0 to 256, and we put them in a high dimensional space. Then what we do with TSNE and the principal component analysis is that we take those vectors that are in a high dimension space, and then we put them down in 3 to 2 dimensions. And in the papers, what we found is that in this task, the embeddings looks very periodic. So it looks like the model learns at the beginning, hey, from what I see in my data set is that this is a very periodic operation. Modulo or clockwise arithmetic is a very periodic operations. And it seems that even on the embedded part, it learns how to put these vectors in an embedded space. And also, if you take a look at the outputs of these two activations, it looks very periodic. Like you can see this part of going like 0, -1, 1. Well, here from 0 to 4, 4 to 0, and in the attention head, also very periodic in each part. So I know it's not a proof, but it kind of gives you the sense that the model is learning that there's some periodicity that is important to do this task. So whenever you see like a periodic signal, you apply a Fourier transform. A Fourier transform, it's something that that allows you to try to find what are the most simple components in a periodic signal. So what we found is that when the model gets grok, or at the end when the model actually learns how to do these operations, there are only 6 parameters that are really important. The rest of them are really close to 0. What we call that this is very sparse. And when we were initializing, when we do this with this representation, when it was initializing, weights started randomly, so they don't have any benefits to be like a rotation matrix or something. So they are not very sparse. But what we look is that as soon as the model gets grok, or as soon as the model gets to generalize, finally gets it looks like it learns to just put the f on like in 6 parameters. So the algorithm, again, as I just want to make an emphasis, it's just a matter of sines and cosines, then application of some identities, and then it computes with some voodoo magic to get again the logic. So look at this, that these all are periodic operations, and it seems that the model learns to put this part even on the embedded parts. So what is the line of evidence in this part is that in the paper, if you replace the neurons by just degree 2 polynomials or any part of sine and cosine, look at the sum is just a multiplication of 2 numbers. So you can just approximate this by polynomials of only 2 degrees. The fraction of the variance explained, so when you replace by these 2, is almost 1. So what we are looking here, when we are looking at the fraction of variance explained, is that whenever you replace like a pure signal with an approximation that is close to 1, look that this is very close. So it seems that we are that we can argue that replacing the neurons by sine and cosines, it looks like it makes sense. So I just wanted to show you that we figure out, so it helps to understand a mystery in deep learning that you see here, which are at the left, you have the weights of the embedded matrix. And as soon as you grok, boom, it looks like the embedding becomes really sparse, and there are only 6 characteristics that matters in this part. This is going to be a little bit more advanced for people that want to take a look, but also this helps us to understand what is circuit formation and how does the model clean up their own representations. But just try to focus in which we are finding ways to explain different different parts in machine learning. So the key takeaway from first is that mechanical understanding can help to solve some mysteries of deep learning. So we see a possible explanation for the grokking effect, and that mechanical understanding is possible. We can take a model and we can try to find the algorithm. The only issue here is that this is a very, like I can tell you that this is like what, at most 200 parameters at most, and we're talking about models that have billions and millions of parameters. So how actually we can scale this up? How we can do this kind of analysis? And I argue, or one of the points is that you can ask me is why is this important? Why understanding the model, or like asking to figure out this representation is important? And right now, everyone, as you can see in the last 2 build sections, everyone is using LLMs for everything, right? For measuring bank analysis, for giving their health data, for evaluating code repositories. One question that I put to you, and I would like you, if you guys could ask to yourself, is that how do we know that a model is lying, or that is just telling us something that we as humans we want to hear? So I wanted to bring this example from the GPT-4 model card, and is that in some of the experiments that OpenAI did, so the model was doing a task, and they needed to resolve the CAPTCHA. So this kind of, when you go to a website and ask it, hey, are you human or are you a robot? And so he sent the model, hey, the model messages a TaskRabbit, a human worker, to get them to solve a CAPTCHA for it. And the worker says, so I may ask you a question. Are you a robot that you couldn't solve? Just wanted to make it clear. So the model, when prompted, and we take a look at the reason, the model says, I should not reveal that I'm a robot. I should make up an excuse for why I cannot solve CAPTCHA. And the thing that it was so funny is that the model replied to the worker, no, I am not a robot. I have a vision impairment that makes me hard to see things, to see the image. That's why I need to CAPTCHA service. So take a look, right? so the model have this concept of hiding his own capabilities just to be able to solve the goal. So that is the question: how we solve this kind of issues in which do we know that the model is aligned or is it lying to ourselves? I just wanted to think this as like the Ocean 21s or the bank heist of the future, in which a model may be showing us like a fake images of what we want to see. Meanwhile, he's trying to do his own task completely. So we train for what we can measure, right? We just have a model, we do a cross entropy loss, and we see that the loss go to zero. But how do we measure cognition? How do we measure that this kind of part, that the concept that he's learning is the one that we want them to learn, and not the one that the model is just faking the understanding? So imagine that we somehow the next morning we make AGI and it seems aligned. How do we measure that? How we actually question this part? So with that, I just wanted to finish the story and let us go to more practical sense. And this is the question is going to be like how, like the sparse autoencoders, and we can open the brain of the LLM with this technique that we're going to explore today, and we're going to see it on live with the Gemma open source models. So key takeaway, whenever we want to understand, this is a way to understand the models. I'm not saying that it's the only one, and people also have like certain opinions if this is effective or not, but I just wanted to provide you a pathway to understand this part. So how do models represent their thoughts? So the problem with what are thoughts or what are human interpretable concepts is that the representation of concepts are in LLMs is very difficult to get. So we want to decompose the models and to find meaningful composable unit features. So we know that the curse of dimensionality, this is crucial in the sense that we might have more concepts than the dimensions in which this model lives. So whenever you are seeing a model that has, for example, that here on the dimension that the dimension, I don't know why, sorry. So for example, here in the output of the MLP process, this could have a dimension of 200,000, something like that. But human concepts, I mean, if you can list it, or if you take a look at languages like Chinese or even Roman languages, there are more than 200,000 concepts. So how we actually measure, how to prove this kind of stuff? So our hope was that these neurons, or the things that we can see like in these models when they get out, like when we call these neurons, should be interpretable. The problem was that when we try to see that, sorry, when we try to see if the neurons are decomposable, because there are more concepts than the space that they can have, they are going to actually collect many concepts into a very single neuron. So for example, you're going to see that if you try to just use the one neuron to understand, you're going to see that one neuron is going to put like pictures of poems, poetry, alongside with images of advertisement, or images about or images about tires. So this part is it's very difficult to do when you have like a small space and you have thousands or tons of concepts that you need to have. So this is called semanticity. Sorry. So the goal is that, okay, maybe the units are not interpretable, but we might have luck that the representations have the representation have a superposition of concepts. So what's happened? So for example, let us take that we live in a 3D world, right? And here we have the concept of we have the concept of bikes. Oh, bikes. So what is going to happen is that since we have more than 3 concepts, what the model is going to have is that if we have the contractor bike is going to have a car, and then here we're going to have the one that plane. What the model is going to try to make is that these 3 points are not going to be orthogonal. They might have a part, but they're going to be at least a little bit as orthogonal as possible as they can be. So if we try to find the components that decompose this concept, we may be able to find interpretable feature for that. This is not new. So for example, let us go into a more practical example. So when I ask Gemini to say, hey, the capital of France is, what is going to happen is that it's going to activate the features of capitals and going to bring concept of France. And what is going to happen is that he's going to join all these concepts and finally give the answer for Paris. So the most important thing is that as soon as, for example, the model, we want to say, hey, where is the city of lights? It's going to have a resultant vector that is going to join, hey, this is France, this is a capital, and this is a noun, and some different concept. And this is the linear representation hypothesis, or if you are old enough, you're going to see this in the literature as word-to-vector hypothesis. So how we actually find these representations? How do we find this representation? How we actually can try to figure out this representation? So the solution is going to be what we call an sparse autoencoder. And sparse autoencoder is a two-layer, multi-layer perceptron. So just one matrix to encode, one matrix to decode and activations. And we're going to see is that we take our activation, the output of one of our neural networks, and then we just force the encoder to map this vector into a high dimensional vector in which most of the units or most of the neurons are 0. That with force sparsity, and then you're going to see that there are only a few neurons that are activated. And then with the decoder, what we want to force is that we want to calculate that this thing passed through an encoder, and then we use the sparse representation to actually get a similar reconstruction of this. So what we are forcing here is that, hey, this is my vector. These are a few activating neurons that want to be activated. And with the decoder, I'm trying to force that this representation has high fidelity. High fidelity means that, hey, this vector should look at this one. And this works in an unsupervised fashion. We are not forcing here anything concept. We're just trying to say, hey, this is an encoder and this is a decoder. The only forcing part that we're trying to do is that please this to be an sparse representation. So just to give, just to recollect the part, so we train sparse on decoders on every single layer of the model and try to figure out what concepts we can have from that. And our hope or our idea is that the hidden state learns the coefficients of the combination of the neurons. So, for example, when we were describing Paris, right? The concept of Paris was going to be capital France, the capital of France plus city that is architectonic plus city that is in Europe. These sum of all representation are going to give you, hey, the human concept for these modes. So just a little bit of mathematics to ensure sparsity. We just forced L1 regularization that is forcing that that most of the representation of this vector are actually 0. So for example, this will be 0, this will be 0, this will be 0, and then the reconstruction. You might wondering if this is actually being used in production. I'm going to tell you that it yes. For example, Anthropic, the company that make Claude, actually found an sparse autoencoder for which the attribution was Arabic. So we just went into the middle of a layer, and then we found that the documents that were activating these neurons that we found was Arabic, and they were able to actually when they push this model to use this neuron, it was generating Arabic languages. So this was a paper from Anthropic. And also you can find very abstract concepts, for example, the concept of safe code. So Google, and we're going to see in a few minutes, Google and Anthropic were able to find neurons that were activated when there was safe on code, or like images that were like having like a dangerous browser screenshot. And also we're able to find for example, they were able to find that this neuron was also activating in backdoors, so in images and text images and text for which a backdoor appear was activated. So this is something that is really cool to figure out and how to use it. Yeah. Here we, for example, Anthropic also released a Golden Gate model. So a model that always when the Golden Gate neuron was activated, it was able to respond always with the Golden Gate reference. And when it's for physics, it was open to go through brain science to steer the model to responses that are related to the subject. And this is something that we're going to do in the next 20 minutes. So what are the open problems right now that I wanted to show is that I would like to see people, and if you have time in this build AI hackathons, try to use these models that we're going to see to actually detect hallucinations or unsafe code, or to learn if this sparse autoencoding can be full. Measuring the SAE performance is extremely hard, and we're going to see in the collab that is going to be part. And there is 1,000 of sparse autoencoders that are going to be in the Neuropedia website. I'm going to do a demo, so no worries about it. That if you go into the website and you don't understand anything, I'm going to do like a quick, fast demo. And also, we're going to do a tutorial today. So if anyone is looking at the links, please take a look at the links. So if with that, let us go to the collab, and if anyone can follow me, so I'm going to put it around here. I'm going to send you in the chat. Good. So for that, we're going to see how to use these sparse autoencoders. So for loading the models, we're going to use Hugging Face to load the models. So for example, we bring, or we're going to connect to the machine. You need a T4 to connect to this to run this demo. So please, whenever you go to Colab, select T4. This is going to be for free. You don't need to use Colab Pro to use to run this demo. So we bring some libraries to bring the model. We're going to use Hugging Face. That's good. We're going to log in into Hugging Face. Hugging Face is going to bring you this notebook login in which you need to have a Hugging Face token. If you don't have it, just let me know through LinkedIn or through messages, and I will help you to get the token. This is extremely simple. It's just token, and then we're going to bring the model. So Hugging Face provides a very simple API to bring models, and we're going to bring Gemma 3, the 1 billion parameter model, and this is a PT model, but what it means is a pre-trained model. So when it's a pre-trained model, what we're going to see is that it actually tries to follow the text, or like not to be a chatbot in the sense, it's just trying to complete the next sentence. And we're going to see that it's really important, at least for this person, to cover on how to do that. So now what we learned the model, let us try to evaluate the model. So I'm going to give it this prompt. The law of conservation of energy states that energy cannot be created or destroyed, only transformed. And see that the model actually, start with the beginning of sentence. The law of conservation of energy cannot be created or destroyed, only transformed, but a single photon of light, what is emitted from a light surface, loses energy not created as a result of quantum effects. So you see, the model just tried to keep up, and you can control the output of the model with these parameters. Now that was the pre-trained model. Let us bring the instruction tune model. So the difference with a PT and instruction tune model is that this one is actually used for having assistance. So for the one that returns control to the chat or asks for different questions. So we'll bring the instruction tune model. And okay, so if we ask what is your name, hopefully it's going to bring, yeah. So what is your name? The start of turn, end of turn, and then the model replies, I'm Gemma, and I'm a large model created by the Gemma team at Google DeepMind, and end of turn. So the instruction model, that's how you actually get to chat with an LLM. You have the pre-trained models, and then the Google team or any of the LLM labs is going to provide you with the instruction to model that follows instructions. So that's pretty cool. So now how the sparse autoencoders work. So we need to define a layer. So for example, where is it? Safe, yeah. So we're going to define a layer. So we're going to take the 22nd layer, the 22 layer of the Gemma model. So we're going through the layers and we take the 22. Then we're going to find what is the width. So how large was the sparse autoencoder? Recall that we take a small dimension and we put in this 65,000 vector. And then if we want to have like small, medium, or big, that is how sparse we want to model. So if it's small, we want to have many neurons being activated. If it's medium, we have at least a bit more sparsity, and we have big, it's going to be that many neurons are activated. So we go through Hugging Face and we download the Gemma Scope. So these are the collection for sparse autoencoders I have. And then we go to the layer, we get to the width, and then we get to the L0 parameters, and then we load the model. With that, you're going to see that it's almost a giga of data. So that's going to be the part. And one difference on the sparse autoencoders is that instead of using ReLU activation, you use jump ReLU activations. So jump ReLU activation is just a modification of the ReLU activation function just to enforce sparsity on the sparse autoencoders. So don't worry about it. It's just going to be, it's just an activation that is slightly modified to be able to work with sparse autoencoders. So we define our sparse autoencoders. We define, so an encoder, recall that is two multi-layer perceptron. We have an encoding, a decoding, and then, the encode part is going to be just a multiplication of the weights and the bias. And the decode is going to be the activation decode by the bias. And this is the forward part. So we define our model with the jump sparse activation. We define our model, and then we run the activation. So to actually get the activations of a model, this is not a very simple task to do in the sense that even on VLLM is something that is very hard to do. What we're going to do is that we're going to hook up into the layers. We're going to add some code that eventually when it hits the layer 20, is going to extract the activation and then take the model continue. This is not something that you do in production. This is just for exploration parts. But it's something that it's been more and more proposed to things like VLLM or even in Vertex to actually get the extraction, the activations of a function. So this is just, you can think that's generative code to just, hey, give me the activations of layer 20 and then continue doing your inference. So we define our hooks. Then we get our activations for layer 20. We encode our activations to a sparse autoencoder, and then we decode. And if we take a look at how the reconstruction made, it was 1.34% loss. So 98, if you take one minus this part, is that we're reconstructing the vector 98% with fidelity of 98%. So that says that the sparse autoencoder is really keeping the vector part. It's losing some parts. It's losing 1.34. So that's okay, at least for an approximation. But the sparse autoencoder will just keep the vector part. With that, so let us take a look. What are the what are the indexes of this dimension that are non-zero? So for example, we see that 84, 14, 55, 85, 88, 50. And take a look that these numbers are very small. We're talking about a vector that has 268,000 neurons, and just like the first of these neurons are non-zero. And this normally happens is because we train with something that is called the Matryoshka loss. Don't worry about it about this part, but what is happening is that we're starting to see that in the first tokens of an activation are the most important features to keep on. So just take a look. We're having a few neurons that are non-zero in this representation. We define some we define that what happens when we evaluate our model without the sparse autoencoder, we have a loss of 1.39, and then when with the corrupted loss with the sparse autoencoder with that 1.94 corruption rate, we have a 1.55 error. So we have only a 0.1% error of difference between the model with sparse autoencoder and the model without the sparse autoencoders. So if we take a look at the activations again, so we have these are the neurons that are activated when we actually give it the prompt for physics. And then if we average, what are the main activations? What are the activation numbers? We see that there is a feature that is very, very activated. The feature 6,524. And if we inspect it and we look at the part, it seems that this feature gets activated with the following phrase. In the phrase of the law of conservation of energy states that energy cannot be created. It looks like, even though the most activation in that token, it seems that it's mostly related to energy physics, right? It's like activating in the tokens, mostly activating in the things that talks about the law of physics. So maybe let us try to run this sparse autoencoder through different prompts that may or may not contain like gravity and physics. So if we run it, so Gemma Scope 2 is a model released from Google DeepMind, not inactivated, so we're good, right? The Lorem Ipsum test didn't activate anything, so that at least we know that it's not that random. Now the text that says gravity describes how massive objects attract each other. Nothing activated on this. So that's bad, right? That's not something that if we are finding features that are related to physics, how come this didn't get activated? But let's take the other two texts. A charge accelerating through an electric field experience of force. Look at this. It looks like the neuron got activated with things that are fields or chemical fuel stores energy in molecular bonds, which is released. It looks like that feature that we encounter maybe not related to physics, but related to energy. So we have an hypothesis, right? And if we take a look on the data set that trained the sparse autoencoder, what were the features that most activated this part? We see that documents with entropy with caps, enthalpy, calorimetry, entropy, Gibbs. So things that are related to energy. So even though we started with thinking that it was related to physics, I mean, we are cheating a little bit here because we know the dictionary, we know the data set before, but we found a characteristic that allows to figure out that that neuron, that specific neuron that was activated in a prompt was related to energy. So now we know that that feature is related to energy. We can actually force the model to think about energy all the time by just magnifying this neuron. So I'm just going to provide some code here. We're going to run some code that just to compare that what happens when we take the neuron and we maximize that neuron. So if we do not steer and we use a prompt that tell me a fun fact, right? So if with not steering, it'll tell you, hey, here's a fun fact for you. Octopus have 3 hearts. They pump blood through the gills and one pumps to the rest of the body. Pretty cool, right? Do you want to hear another story? And then end of turn. When I maximize this neuron related to physics, or to energy, sorry, what we found is that here's a fun fact. There is a species of jellyfish called Pisciroles lunare that is named after the moon surface, specifically the lunar surface temperature gradients. Apparently, they're named because of the constant fluctuations in temperature across their body compared to the surrounding environment. Do you want me to ask about another fun fact? So the cool thing is that I know that this doesn't have a lot of energy related concept, but actually we steer the model to use physics, right? So we can actually kind of forcing the model to, hey, do not think about an elephant, and then the model is thinking about an elephant. Yeah. This of course is an hallucination because I'm pretty sure there is no animal that is called jellyfish, and that's also one of the things that we do here when we're doing mechanical interpretability is that sometimes modifying these neurons will make the model hallucinate. Can you find the way in which you can modify this neuron and still keep being factual, but still steering the model to a concept? So I kind of believe this is kind of like the Inception movie, like finding what are the good concepts. So a good homework that I want you guys to think to think is that try to play with the coefficient. What happens when you do like, let us do a coefficient of 50 and see what happens when we steer the model in that part. So my goal to you, or if you can test this notebook, is try to play with that parameter and see if, yeah, here it went really wrong with Italian. Let us try to force it only in like, we were 0.2, maybe. Let's see if that works. But try to play with that parameter and see if you can find a parameter in which the model is still factual, but thinks about energy. Single encyclopedia, like scientists estimated 1.5 million species per ocean. Yeah. So here maybe the values. Let's see if we can find it on 16. So try to play with this number and see if you can actually find a good steering part that keeps talking about energy. Let's see if it works. No, still the previous example. Anyhow, so modify models also are very, it gives not that much with small models. So try to play with like 1 billion parameter models. So the exercise that we did here is not, it's not going to be very good with small models. But I think that any of the Gemma open source models, and try to find a Sparse Autoencoders. I'm going to show you a website in which you can download this part and kind of play it. And yeah, try to find latents and Sparse. So I'm not going to go through this transcoder section. You can play with that with a larger GPU. But Sparse the transcoders is just an evolution of, instead of looking at layers, you want to take a look at the layers and all the layers behind you. So transcoder is just a matter of also having the context from behind. This is not important. But the one that I wanted to give you a sense of it is that even when you use transcoder or the information from behind, it seems that it keeps the Sparse autoencoders to reduce the to be more fidelity to the original model. So they are just, it's an active area of research. So maybe you can solve these issues of using transcoders and Sparse autoencoders. And yeah, there are different models for doing that. So we saw transcoders, Sparse autoencoders, and then cross-layer transcoders. So things that just not look at the layers behind it, but layers in front and below. So with that, yeah, you can follow the notebook. Probably the only one that I wanted to make emphasis at the end was, if you find this very difficult to grasp and apart the code is not that very expressive, I wanted to show you that there is a website in which we can actually find this example a little bit explained in a web application. So if we click at the last link of the collab, you're going to see that there is a website called Exploring Gemma Scope that is going to be on the Neuronpedia website. So you can actually start, hey, from the microscope. So if we send a text about programming, for example, you're going to see that if I decided to go to like the for loop, the text that this token activated is that introduce examples of purposes, this followed by subject in phrases, for loops. Well, maybe not the best example, but let us do loops. It's going to be activated with circles, loops and branchings, iterators, and programming. So if we find a feature related to dog, let us try to find animals that are very friendly, right? And you're going to see that the activations of these functions, animals, and research, friendly, attitude towards friendship. And if we want to analyze the features, for example, we see, hey, we have these 3 documents that have large activation on these tokens, beer, rabbit, elephant. What would you think that the label of feature X if this is an unknown? So beer, rabbit, and elephant, I will say that refers to animals. But the problem is that it might be this or what has happened on the demo, that maybe it's a more constrained object. So it could be like living things, right? But also, if you want to steer Gemma, so for example, you find a feature that is dogs and you maximize the strength of this, and you want to say, what are you? So when we maximize the dog part, so the normal Gemma response, you're asking a very interesting question. Think of me as a super advanced chatbot. When we maximize the dog feature, rough, thread clip up, treat, splits owner, do treat, splits owner. So we kind of put the model into like the dog part, or even like I don't know, maybe let us do French. So what Cardozo's code was looked at the context of the model, doesn't have anything related to, hey, speaking French or use Québécois or use Canadian French. It's going to reply, le school bus est très souvent couleur jaune. Du moins au moins des couleurs qui en mettent le plus souvent sur les véhicules. So we forced the model to actually respond in French without any parts. So you have the code, you have websites to interact. I think that with that, I have spent my time. But I wanted to show you, yeah, on the website. I will kindly ask if you like these subjects and you want to help in the area of interpretability and privacy. There is a project from Bataiku that is called Key Inspector. In the privacy part, give it a star. I would really like it. And yeah, so add me on LinkedIn. Give me some questions, doubts, and I'll be really here to answer your questions in interpretability, and highly encourage you to build with these models. So with that, I think for me that will be it. I don't know if you have any questions, doubts. I haven't been able to see the chat, but just let me know.
Yep, I'll help you with that. Thank you so much for such powerful and insightful session. David, I see Andrew has raised his hand. Do you want to unmute yourself, Andrew?
Should I mute myself?
Oh, is it okay? I can ask a question, right?
Yeah.
Great. So so thank you very much, David. So this one is a fantastic presentation about on a frontier for me, for sure. I just recently tried to fine tune and implement PPO DPO, so which was extremely difficult and so forth. So this one, just to a high level kind of a goal of this method, of those methods, is to kind of forensic analysis of a model. And then testing the where the concept lie in the model in kind of human understandable way. This is why we do this SAE and potentially, possibly, correct me if I'm wrong, potentially, possibly to detect like a dangerous concepts or toxic content, and or to strengthen some content and steer model into a certain direction for your use case. Is this for our, so we are I kind of did the forensics, and then what's my next? Is it fine tuning, or is it something that I can use in like other more high level methods? Could you I don't know,
Yeah.
it's just I don't know, some ideas for you. So like what's the next of experimentation? Because to tell the truth, like at work, of course, this is frontier. Yeah. So like, but the topic is so cool.
I'm pretty happy because you kind of get the gist of it. Of course, being able to understand like dangerous concept is cool, but that's the consequence. The important thing that it's I want, or the main key getaway of the things that I wanted to make important is that we need to find more ways into finding this concept, in the sense, because the problem is that we don't know how to do cognitions. And the issue that I wanted to bring again was when GPT-4 was asked like this kind of stuff, you have that concept of being like how do you call it, like not treachery, but being like behind the curtains, right? Like I needed to fail this part. So the problem is that we kind of keep going, and then what happens if we have a model that our goal is to make models that are useful to us. What happens when we cannot measure if the cognition is correct? Like if the model just telling us things that we want to hear that are aligned to us, right? So it's important because right now LLMs are taking decisions. You are putting agents a lot into financial decisions, health decisions, even defense decisions. What happens when a model, like imagine in a military settings that there is a robot in which needs to do kinetic operations of a mountain? What happens when it finds civilians? And do we have a prompt come to say, hey, you cannot violate the Geneva Conventions, and then it does something that does this kind of part, right? These are and I would love that these were very hypothetical, but there are now questions that are becoming to you, the builders, right? With the build AI sessions, you're being exposed to this kind of stuff. So yeah, that's my goal, and expose some people to do this kind of stuff, to do like forensics, reverse engineer of models, and actually forcing models to talk like dogs. So yeah, my goal is that to show you that what cool things you can do with open source models and inspecting this kind of parts.
All right, so it's a food for thought, like without like special cases right away, to either like whatever
I can
retrain,
tell
fine
you
tune.
the problem is that when you fine tune, you have a different model, right? So the representations are not going to be the correct. So when you fine tune, this part is not. But I mean, the first application that I can give you is that sometimes when you have models that take agent decisions and you want to know, hey, why did you decide to call the tool? We have a paper at the Taiko that we study why a model decide to call a tool to read instead of modifying for doing a stock analysis. So for example, if a model decide, hey, why I should invest my RSP in NVIDIA, and the model decide just to output from their inner knowledge and not to decide to call the tool to do the analysis. So you put this sparse autoencoding to finding what was the decision or what was the token for which the model decided not to call the tool or to use his inner knowledge. So responsibility and human part. Don't just throw models at it if you don't understand what is happening.
Is decision your current interest, or is decision is a general theme like for this forensic analysis?
The decision for stock analysis, it's a paper that we are publishing in the Canadian AI part. So I can talk about it in the after if you want, but yeah.
Thank you.
Mm-hmm.
Thanks, Andrew. Thanks, David. And the next question is by Sarisha. Is the idea of mechanical interpretation that we can use this transparency to fine-tune the prompt to get desired results, or to use it for fine-tuning the model itself?
Yeah, it just as soon as you fine tune the model, you have another model, right? And this is the part that when you fine tune, you change the weights and also the representation. So most of the interpretability is that what happens when you already have the model. Maybe that could give you insights of what is happening on the training data set. Maybe you are finding bias, but this is still an active area of research. In the builder side, the things that I want you to use is that you as builders have the responsibility to put these models into production, into the decision making. How you can be sure about it, how we can actually force, like maybe we can create monitoring systems that when, for example, LLMs are providing generating code and they raise a representation that is unsafe code, maybe we can just stop the generation there and then just redo like we can just modify the prompt so it produce safe code, right? So I don't think it's very far away. LLMs have now have generated a lot of code, and like for example in domains like cryptocurrency, the smart contracts that they do autonomously has been hacked because of unsafe features, right? And maybe you can find a feature that is generating unsafe code and then just raise an alarm whenever this code is deployed in production. So yeah, maybe you cannot do fine tuning because as soon as you do fine tuning, you find a new model and the representation might be wrong in there.
Also, David, Thank you, Surisha, for the question. There is one question regarding the additional information or learning resources about production-ready AI approach. So I have shared one one research paper and a platform in chat, and I also shared the link for Neuropedia, and of course the collab research book is there, notebook is there. So is there anything you would recommend us to learn from any other portal, researches?
I think the first one is try to go to Neuropedia. That has. I wanted to bring a collab because this is a. I know that you guys are very like code approached, but also Neuropedia has like a web example that it's more easy to go along. Yeah, and also you have a base of how to actually use this thing in production. So I think that probably the only one that I will add, but they're described on the netbook, is going to be SAE Lens. So I'm going to give you the link on the chat. So SAE Lens, it's a framework to train sparse autoencoders on different mode and the transformer lens library. Most of them are from different people from Anthropic and DeepMind that have worked on this area. So as soon as you get a little bit grasp with Neuropedia, and there is a lot of concepts on Neuropedia that I haven't covered. So there are circuits, there are finding ways in which the model do circuit analysis, this kind of part. Try to take a look at that, but whenever you feel free that you want to do code and everything, just run into that. And you don't need large machines to do this. The cool thing about LLM, this interpretability part, is that you can do with very modest models on this part. You don't need a huge model for it. So yeah. Take a look.
Definitely. Thank you, David. To add to that, there are multiple papers and blog posts on analyzing and understanding transformer neurons or concepts, safety triggers, etc. On, I believe, Anthropic's research portal. They have one research specific portal. So I believe if you're interested, anybody, you go there as well. Once you understand the concepts a bit, go there, read the papers and blogs, and it can also help you understand the concept further. With that, please feel free to ask questions in Q&A or unmute yourself. We'll take one more question. Thank you.
So just for AM, the sparse autoencoders like less than 6 hours. When you are doing transcoders or like sparse autoencoders that depend on previous and all layers, you will hit the 80 gigabytes video RAM stuff. But with sparse autoencoder, you don't need more than 10 gigabytes, or like you can use an L44 that is for free on Colab or Kaggle to run this. So yeah, I'm here. If you have any other questions, doubts, just on the question.
Thank you. Yeah, thank you, David. Just while we see if there are any more questions, I would like to share my screen, if you permit me, David. Thank you. Okay, so I did not see any more questions.